Now it's recording, I believe. Yes, so let me start by introducing now today's speaker, Andreas Kyprianou, who is one of the very active contemporary probabilists, and he's also very active in organizing various events and seminars. And just a couple of words, just in case. So Andreas, I believe, got his PhD from Sheffield about 27 years ago. And he worked in several different places in Edinburgh and in the Netherlands. And now he's moving from Bath to Warwick. And he made a lot of contributions, I believe, originally to the theory of branching process, but then also to financial mathematics, ruin theory, and theory of Lévy process. So today he is giving a talk on attraction to and repulsion from, and then there are too many words for me to read. Andreas, the screen is yours. Thank you.
Thank you very much. Thanks. Okay, so thanks for the invite. And of course, this is wonderful. And I don't know why it took a pandemic for us to realize we can do these seminars across the world. But I'm really pleased, and I do participate a lot in these international seminars. I think they're fantastic and a good way to connect with colleagues. Okay, so this is work. There are 3 co-authors here. And so Tsogi was from Mongolia. I don't know if some of you remember, I ran out in 2015 a huge workshop in Ulaanbaatar, and then I met Tsogi, and then she ended up becoming my PhD student. Sandra was a postdoc of mine from Mexico, and Matthias Kwasnicki, he's a potential analyst from the Polish school in Wrocław. And we wrote this entire paper online, and there's a unique, given the location of everybody in this collaboration, there's actually a unique time in the day that you can meet with somebody from Mongolia, Mexico, and Poland, and me in the UK, and that's 1 o'clock GMT. So we had to meet every time. This was written precisely at 1 o'clock every time we met. Okay, so this is about stable processes in high dimension, and specifically isotropic stable processes. So I'll just quickly whiz through what I mean by that. So most of you, just looking across the names here, I think most of you understand what a Lévy process is. So a process with stationary and independent increments. An isotropic stable process, so it's a very specific class. It has a stability property, which means essentially we're talking about a characteristic exponent, a Lévy-Hintschen exponent for a Lévy process, which looks like this. And fundamentally, the jump measure is proportional, has density with, this is Lebesgue, by the way, d-dimensional Lebesgue, with respect to 1 over mod y to the alpha plus d. Just to connect to the usual 1 over, you're probably more used to seeing that. So this is if you write it in polar coordinates. So if you think of, and we're going to use this idea quite a lot during the talk, if you think of generalized polar coordinates, so every point in space, you can go out, pick a point on the sphere, on the unit sphere, that tells you a direction to go out, and then you move out a distance r. So up to a constant, if you put the Jacobian in for the change of variables, then you'll end up with the usual 1 over the radial distance to the power 1 plus r dr, and then this is a uniform pick over the sphere. Okay, so usual Markovian notation, so P sub x means starting the process from x. And I had these pictures lying around. I can't remember who did them for me. It's maybe a student. So this is a 2-dimensional path of a stable Lévy process, an isotropic stable Lévy with alpha, the scaling index 1.2. And this is just to give you a mental picture, because I draw a picture later on just to give you a sense of what the paths look like. Here's another one with alpha 0.9. So typically, and this is actually very typical for Lévy process in general, you get lots of tiny small jumps, and then the process will jump to a far location. And in this case, we get the heavy-tailed size jumps. We cluster around here, and then we make another jump, and so on. So there's no time in these pictures. This is just the range of the process over some time horizon. So I don't know in which order these points are visited. This is just the range of where it's been. Okay, so the reason why I've shown you those pictures is so that this picture makes sense. So in the last few years, I've been working on self-similar Markov processes and trying to understand what we can do with them. It's a class of processes I'll introduce in a moment. You need a bit of power here. But a stable process is a kind of classical example of a self-similar Markov process. So this particular talk is about conditionings, partly because that tells us something about the harmonic functions. It tells us something that we're familiar with in one dimensions about Lévy processes, because a stable process is also a Lévy. So this kind of gives us some sense of how we lift that theory out into a bigger category of processes. And it also tells us something, as you'll see, about how to work with self-similar processes and how to take advantage of the definition of the process as a self-similar Markov process rather than just as a Lévy process. So what I want to do is I want to take a patch on the unit sphere, and I want to condition the path to continuously hit this patch from the outside of the sphere. Okay, so I don't want it to come inside the sphere as it approaches the patch. I want it to both stay outside of the sphere and to approach continuously the patch. So what do I mean by continuously? The paths are CAD-lag, but that doesn't stop me asking for a limit and a lifetime at the limit where it hits a terminal point. A terminal point somewhere on the patch. And later on in the talk, I'll deal with the case of hitting the patch when I do allow it to go inside the sphere as well. Okay, so let me just motivate why I said this was somehow connected to Lévy processes, conditions that Lévy process, some work that was done in the 90s, also for random walks as well, preceding that as well in the 80s. So as a self-similar Markov process, a self-similar Markov process has the property that if I scale it with I take a constant, any constant, xt is going to be my self-similar Markov process. Let's suppose I index where it starts from with the little x here. If I scale it in time and space, so alpha will be the index of self-similarity. So if I take this process, I scale, this is the defining property of a self-similar Markov process. I take it, I scale it in time and space thus with any constant, then the process is equal in law to itself, with the one small exception that if I start at x, then scaling it, obviously I need to start at c times x. Of course, if x is 0, which is the usual way this is stated, then you still start from 0 in the scaled version. So a stable process, a stable Lévy process has this property, as you all know. Brownian motion does it, and stable processes do it with alpha between 0 and 2. But I can also use this as a defining property of a class of Markov processes as well. And so stable processes fit into this class. And one of the important properties, which hasn't really had much discussion, it's only in effect the last 5 or so years where we've understood this correctly. Anything that fits in this class of self-similar Markov processes can be written as the following decomposition. Now, there's a lot here to digest. So this pair is a Markov additive process. So it has conditional stationary independent increments. So it's almost the pair sine theta is almost a Lévy process. But some of you might know it as a Markov modulated process. This theta here, it lives on this SD minus 1. I should have said that X is going to be an RD. And this guy here lives in R. So in effect, this, if we just temporarily ignore this time change here, what this is saying I'm writing X in terms of spherical polar coordinates. This is the radius, the radial distance, and this is the identification of the argument of X on the sphere. So a bit like I said before, every point, just if I use this sphere we've got here on the screen, every point in space can always be identified. First, choose a point on the unit sphere, and that will be my theta, and then choose a radial distance to project out in that direction, and I can access every point in RD that way. So the radial distance will be this e to the psi here. And the last thing to tell you will be the time change, but this is less important when one is thinking about range time change. So, oops, it's the inverse of this clock. Okay. It's a bit of a nasty one, but once you get used to working with it, it's not too bad. So the important thing is that, in fact, this turns out to be a bijection between this class and this representation here. So conversely, if you give me any Markov additive process living on this space, then if I plug it into this formula, the X I get is a self-similar Markov process as well. Okay, now I should technically give you a little more detail about this, but if you're willing to accept it from me, think of this as a Lévy process with characteristics that are modulated by this theta. So this theta doesn't need to be a Markov chain. It can in general be a general Markov process that lives on the sphere. Okay, and it can also be jumping around on the sphere as well. All right, so really, once we have this picture in our head, when I'm asking this thing to condition to hit this patch continuously, what I'm really doing is I'm conditioning this psi here, forget the time change for now, I'm conditioning this psi here to hit 0 from above continuously, right? And while I'm at it, I'm restricting where this theta is going. The theta is going to stay in the patch. I'm going to say, make sure this thing hits 0 continuously, but while you're at it, do it with this thing in the patch. And that's reminiscent of some classical work for Lévy processes and for random walks in a kind of different way. Some scaling would be required. So there's some work of Chaumont, for example, which was around the time people were looking at Lévy processes conditioned to stay positive. And Loic, he considered conditioning Lévy processes to continuously approach the origin and hit the origin. So it's a kind of extension of that if we accept that this is somehow an extension of a Lévy process. Okay, so how do we do this? Well, let's start with the most obvious thing. So what I'm going to do is I'm going to remind you actually that a stable process in high dimension has this property that it's transient. So if you look at its radial distance, it tends to plus infinity. So that means if I just let the process free, so if I were to continue this path, it would go somewhere, but eventually it would head out to the origin, to infinity, sorry. And so in that case, there must be a time when it is at its closest to the origin, right? So its closest radial distance to the origin. So this time up to time t is denoted by this. So the overall, what I call the time of the point of, I should say the time of the point of closest reach to the origin is this g bar infinity. And the name of the game, perhaps, or a good name of the game here would be to condition, a way of conditioning it to continuously approach would be to condition the position at that G bar. I've got numerous options. I could put a skin around my patch. Here's my patch S. So I could extend it, put a skin on the outside. Maybe I could put a skin on the inside. And I could force that point of closest reach to the origin to perhaps catch it in the outer skin, perhaps catch it in the inner skin, perhaps catch it in either outer or inner skin. It doesn't really matter. In the end, it gives the same answer. So I think my next slide adds an extra bullet point here just to say that I will show you the case of conditioning the point of closest reach to hit this outer skin and see what happens. But another way, you don't have to work with the point of closest reach. Another way of doing it is to look at the first passage into the sphere when it first jumps into the sphere. And then when it first jumps into the sphere, that's this one here. So I haven't written what this tau plus is the first. Oh, I have written it. It's there. It's here. The first time it enters the sphere. So I could work with that and say, why don't I condition the point when it first jumps into the sphere to be inside this inner skin? That's a possibility. Or another way I could condition is say, well, just before you jump in, so your left limit when that jump occurs, what about putting that in the outer skin and then squeezing the skin down to 0? Okay, so there are lots of different ways you can do the conditioning. I'm going to go for this. As I said, it always gives the same answer. And my conditioning will take this form. So I'll look at the path. So this is I'm going to generate these probabilities on the space of paths, which are killed or come to a terminus. So they have a natural lifetime. This should be X here. This is great. When you've got the iPad, you can correct all the mistakes in your slides. So what I will do is I'm going to take the limit conditioning on the point of closest reach to be in this outer skin here, in A. I think that's what I've opted for here. Of course, necessarily, the process won't have entered the unit ball as part of that. And I'm looking at events. I'm describing this new probability on events on what's happening up to time t. Okay, so that's how I'm going to try and define it. Let's see what comes out at the end. Well, the reason why I've opted for the point of closest reach is because some recent work with Victor Rivero and a PhD student, Pait Satit Kanitkul from Thailand, we proved we were able to write down the law of the point of closest reach, and that in itself is an interesting problem. So here it is at the bottom of your screen. Okay, so this is saying that you recall I said that the process will faff around and then it will eventually go off to infinity somewhere. So it has a minimal distance, a closest distance to the origin for the entirety of the path. Now, ignore this sphere for now. This is just to give you perspective. The reason why I can get this is because we can actually build an excursion theory, a radial excursion theory for these Markov additive processes, specifically apologies, it's a bit early in the morning. We can build a radial excursion theory for these self-similar Markov processes, specifically stable processes. So we are used to, for example, with random walks and Lévy processes, we're used to building theories looking at excursions, for example, from the minimum. So we would typically, I'll actually draw this permanently. So we typically look at the path and then run the running minimum, which of course is quite a complicated object, even for Brownian motion. And then we pick out the excursions from the minimum, and we know that these form a Poisson point process. Or if you're doing this with random walks, you can pick them out one at a time in order, because there are a finite number of them over a finite time. And then you can build nice theories around ladder properties. And then, of course, you've got your Wiener-Hopf factorization and so on and so forth. So here, instead of running excursions from the minimum, what I can do is I can run excursions from the radial minimum. So I've drawn a random walk type object here just to help you envisage this. So here is where I start. So I draw a sphere of that radius, and then I wait for the path to pass into that sphere. Okay, so there's my first excursion. Now I draw another sphere at that radius, and I wait for the path to enter that sphere. Okay, so every time I'm creating a new radial minimum. So in a sense, it's similar to this story, because if you keep in your mind that decomposition we had, you ignore the time change, which, as I said, is annoying but not disabling. Essentially, every time I make a new radial minimum, this guy here, who's almost a Lévy process, but not quite, makes a new minimum as well. And it's just that this part here is, well, somewhere. Okay, it's somewhere on, if I project this onto the unit sphere, which is what this is here for, then that's what this guy is doing every time I make my new minimum. Okay, so we can build a theory there, and of course this point of closest reach is the last left endpoint of the last excursion, because eventually we'll go off and never come back. We'll never get closer than that point there. So we used excursion theory. We had to build that excursion theory, and we can get exactly this rather pretty formula here. So now it's rather easy to go back to my conditioning, because what I'm conditioning on is something that I know I can calculate explicitly using this thing here. So in particular, if I look at the probability of that event, well, you recall that I've got a patch on a sphere, and I've just lifted it by an amount epsilon. So the point of closest reach in there is essentially, saying, well, it's an integral in Cartesian coordinates that I can convert to an integral in spherical polar coordinates. When I do that, I will end up with something looking like this. So the integral is over theta. X is where I start here. And there's a little bit of, there's something missing here, which should be, if I scrub that for a minute, there should be an integral 0 to epsilon somewhere here. But I'm telling you preemptively that irrespective of what that integral is, which I'm not going to write down, when I scale by epsilon to the alpha minus d, I catch just this integral over the unit sphere. In fact, specifically over the patch. Okay. So when I do the conditioning, so it's the usual Bayes formula with a Markovian projection. So I'm looking at event up to time t. So I write Bayes formula with this event here. I project forward on the top intersection of this and that to xt. So I'm interested in this ratio. I've got full control over that now because they scale top and bottom the same way. Of course, I have to be careful with dominated convergence when I take the limit through, but no problem. And here we get this beautiful Dubh transform where this is the H function here. Okay, so this function we saw in the scaling of this probability appears. And actually, this was the setting really when the patch has got mass. So it has, if you take Lebesgue measure over the surface of the sphere, so if I'm integrating here, this integral I should have said is the unit Lebesgue measure over the surface of the sphere. I can do this calculation again a little more carefully, and I can also have a singularity on the sphere. So I can condition the path to approach a singular point on the sphere. That's also possible as well. Okay, it just changes slightly, it ends up just scrubbing this integral here and just working with the integrand. Okay, and there's the point that I'm hitting. Okay, I'm just going to skip this slide here, and I'm going to go now to the harder problem and talk about conditioning to hit the patch, but this time I will allow the path to come in and out of the sphere as part of the conditioning. Okay, so before I was saying, well, you're not allowed to come inside of the sphere, you have to come to the patch from the outside. Now, in this setting, the point of closest reach isn't a good conditioning event because, well, we use that essentially to deal with the fact I want to keep the process outside of the sphere, but when I'm allowing it to come inside the sphere, that's no good. So I have to go back to a conditioning that's a bit more in the realms of this. So this is the first time now I enter the skin either positive or so outside or inside of the sphere. And I'm going to condition on an event, typically, I should have said this is in the filtration up to time t. I will look at the event, and so I'm going to build these probabilities. I'll look at the event that I condition on something up to time t, conditional on eventually getting into this inner outer skin here as epsilon tends to 0. Now, there is a proviso here. I do need to start restricting my stability index between 0 and 1, because when alpha is between 1 and 2, it turns out some old work of Port or possibly Stone, I can't remember. Stable processes when alpha is between 1 and 2 will hit the sphere, the unit sphere. And that's a little bit in the spirit of the statement that a stable process in one dimension will eventually hit 0, the origin. If this is time and one-dimensional space here. So a higher dimensional version of that is that it will eventually hit the sphere if and only if alpha is between 1 and 2, just as in this case, alpha needs to be between 1 and 2. Sorry, 1 and 2, yes, I wrote 0 and 1 because it's early in the morning, so you'll forgive me for that. Okay, so how are we going to solve this problem? This is a slightly harder problem because I need to understand, in effect, the asymptotics of this hitting probability, the hitting of the inner or outer skin. Well, this is the answer. So again, we of course get a law which is absolutely continuous with respect to the law of the stable process, and it's a Doob H transform. This time the H function looks like this. Just to compare with what it was before. So before it looked like this. So we were hitting a theta in the patch. X was our starting point. Okay. So really, this is the important thing, theta minus x to the power minus d. Whereas in this case where we're allowed to come inside and outside the sphere, it's theta minus x to the power alpha minus d integrated over s, and we've lost this extra function of the starting point x. Okay, ignore this stuff at the bottom. I didn't talk about that earlier, so we don't need to talk about that now. And again, if I say, well, I'm going to hit a singleton on the unit sphere, then this collapses to simply the integrand. And I should say that this now marries up with some previous work about hitting single points. So hitting a single point on the sphere is essentially the same problem as just hitting a single point in space, or conditioning rather to hit a single point in space. And that had been done earlier, also with my PhD student, and of course, we still use this H transform in that setting. So the result follows because we are able to produce the asymptotics of this hitting probability. Remember, this was hitting the skin either side of the patch. And you get this rather exact formula. So this is just a nasty constant here, but there appears the H function. The scaling is epsilon to the alpha minus 1. Earlier, we had a scaling of epsilon to the alpha minus d, and I'll come back to that at the end of the talk. When alpha is 1, it's a little bit harder. The scaling, obviously, if alpha is 1 here, that doesn't say anything. So the scaling becomes the modulus of log epsilon. And again, this is just a nasty constant, but fundamentally, this pulls out of the probability, which gets smaller and smaller. It pulls out this H function. Okay, now the way we prove this is quite different. So you'll see why Matthias was part of our team, because we're going to use some potential analysis here. So here's the name of the game. So a classic result, very old result for isotropic stable processes says that if I want to look at the expected occupation in a small ball dy, so this is the average time I spend hanging around in a dy, then it's proportional to Lebesgue measure dy with this density, mod y to the alpha minus d. That's quite an old result. Now, what I'm going to do momentarily is just detract from the problem at hand. And I'm going to say, let's suppose I have this measure, which I'm going to put some conditions on it in a minute. So I'm going to imagine I've got this magic measure on my patch, which has been fattened up inside and outside of the sphere by a skin of depth epsilon. I want it absolutely continuous with respect to the Lebesgue measure. I don't know why I've started writing LD here. I've been using dy here. And we'll have a density while we're at it, which is written m epsilon. So this object here is called a Reese potential. If I have the things I've asked for here, then my Reese potential looks like this, where I've used this density, occupation density, to my advantage. So this is an occupation density here. And so just by using Fubini's theorem, if I stuck this in there and then change things around, I would, and put the density in here, I would end up with this. Okay, so my Riesz potential looks like that, where this is the density of my desired measure, which I'm going to ask more things of it in a minute. And here's the first thing I'm going to ask more of it. So on the exterior of my skin with a patch, I'm going to say I want this thing to be 0. Okay, now if that's the case, I'm not going to accrue any occupation on the support of this density until I actually enter the patch with its skin. So if I use the Markov property, first I need to get into the patch with the skin, and then I can start looking at the occupation thereafter. And of course, I'm going to apply the Markov property. So I end up with this recursion for this Riesz potential of this measure, which I'm putting more and more requirements on. Okay, so why have I done this? Because if I now further ask for the property that, so I put a requirement outside of the skin, the skin of the patch. Now let's put a requirement inside the skin of the patch. So I'm going to say, I'm now going to ask for this, this measure to, to have the property that inside the skin of the patch, the Riesz potential is exactly 1. If that all these things hold, then over here, because necessarily we're inside the skin of the patch when I first enter, this becomes 1. This becomes the probability of hitting the patch. And I get this identity that says that the probability of hitting the patch is the Riesz potential of the measure that I've asked 100 different things of. So my strategy for looking at the asymptotics of this will be to guess what this measure looks like to leading order. In other words, if I can get a good enough approximation of this, actually the hardest thing that I need is precisely this. I need it to be 1 inside the skin with its epsilon, the skin of the patch, the epsilon skin of the patch. So if I can guess what this should look like, at least asymptotically guess what this looks like in this sense, then that would probably be good enough to produce my asymptotic probability of hitting the patch. In a sense, if I guess what this is by guessing what this is, then I've also got the right-hand side here. So that would tell me asymptotically what I should expect. Okay, so it's a kind of bootstrap argument. I get a coarse guess for my measure mu epsilon, but then this argument here tells me that actually that will give me the probability asymptotically of hitting the patch with its skin. Okay, so how am I going to perform that guess? Okay, so this is where it helps to be a flat Earth theorist. So if you know these guys who think the Earth is flat, so actually this is really helpful in this case. Here is a known identity. And actually, I haven't pulled this out of nowhere. There are 2 places where you would perhaps go looking for this. So one is in what we know about stable processes. In 1 dimension, there was some recent work of Thomas Simon, where he used this identity for reproducing various calculations of Blumenthal, Gator, and Ray from the 60s. And actually, fundamentally, what this identity is saying is that if I split the integral from 0 to 1 and -1 to 0, it's kind of saying there's an f there's an F21 blah, 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 plus, and there's perhaps something in front of it, plus another F21 blah, 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 which is equal to 1. And if you go and look in these reams and reams of tables for hypergeometric functions, you'll quickly realize that there are plenty of identities of this type here. So really, this integral here, if you split it, as I said, between 0 and 1 minus 1, 0, that will give you something that starts to look like an F21 function. And so it's just a linear combination of two F21 functions that's going on there. So what I'm going to do is I'm going to say, okay, I'm a flat earthist now. So I wanted to force, as you recall, I wanted to force my measure to be 1 when I'm in the patch around when I'm in the skin around the patch. So of course, if I'm a flat earthist, whilst I'm in this zone here, I see the Earth as flat, right? So locally, I don't see the curvature of the Earth. So my guess would then be, well, let's think about breaking this is an integral, this is a Rees potential. Let's think about breaking that integral as a radial integral, and then an integral over the patch. And in a sense, my guess is going to be, I'll take this thing here, so I can scale this integral from minus epsilon to epsilon. I'm going to take this because I know it appears in, let's not say analogous, but sufficiently convincingly close scenario in one-dimensional theory of stable processes. I'm going to take that object and I'm just going to say, you know what, I'll just replace the y in the integral here by the modulus of y in high dimension. So I'll have Lebesgue measure in high dimension here. This is the density we spoke about. I'll just adopt my flat Earth perspective. I'm just going to integrate across here using that density there. So that's now the modulus of y. And then I will just restrict the density to being in this patch when I'm talking about the angular part. So let's go with that and see if I can produce this. Well, one other thing before I do that is I kind of don't like this indicator. This indicator is a little bit of a pain. So what I'm going to do is I'm going to say, you know what? If I'm somewhere in here, flat Earth theory tells me, well, look, I'm here in Bath and Australia's over here. Well, it's not even over here. Australia's way off the picture. I don't really care what's going on in Australia. In fact, why don't I just integrate all the way around the Earth here? Why don't I just keep integrating? And my expectation is the contribution from Australia to what's going on in Bath won't really matter. It'll be too minimal. So I'm going to go one further and I'll say, I'll scrub this. I'll just get rid of this. So this will be my guess, actually. This formally is saying this is when I scrub the indicator, and then I've got the difference to deal with later on. So this fundamentally will be my first order guess to see if I can satisfy this. Now, okay, I'm going to put this slide up for about 2 seconds. I need to calculate this. I get into special functions. Of course, I've alluded to that earlier, blah, 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 and it comes out. One needs a bit of patience. So just to rehearse the argument, so now I've got this just by guess and verify. That means that I have this available to me. Remember, I've got now an explicit form from this, from my guess, which is essentially this density here with respect to the Lebesgue measure. That now gives me the theorem here, the asymptotic probability. You're going to see my wife crawling behind me. She's trying to... that gives me the asymptotic probabilities here, which will allow me to construct the conditioning that leads to the DuPage transform here. Okay, now just to finish up, because I think we're approaching time, the same ideas also work with a hyperplane. So rather than conditioning to hit a patch on the sphere, how about taking a hyperplane and just saying, look, let's just try and continuously hit a patch on this hyperplane, allowing, if I draw it on the side here, allowing the path of the stable process to come in and out, above and below rather the hyperplane, rather than in and out of the sphere. So we get the same analysis, and all that changes really is, well, we get nasty constants for these hitting probabilities again, but the fundamental interesting bit here is that the harmonic function that comes out, we replace this was formerly a surface integral over the sphere, over the patch in the sphere. Now it's just a Lebesgue integral over the surface of the hyperplane. Okay, so final remark. So I did allude to this earlier. So we did a couple of calculations. So one looked at the asymptotic hitting probability of the point of closest reach in the outer skin of the patch, and we had to scale by epsilon to the alpha minus d. And then we looked at the asymptotic probability of hitting inner and outer skin of the patch when we can go into the sphere and out of the sphere as we're approaching. And we had to scale by epsilon to the alpha minus 1. I'll exclude the case when alpha is equal to 1, because that's always a bit special. So why do we end up scaling here by alpha minus d and here by alpha minus 1? And this is really from the flat Earth theory. This really is because when I'm conditioning to hit the patch, but I'm not allowing the process to go into the sphere, so I do need to be conscious of the curvature of the Earth, right? I do need to be conscious because in a sense, I could go all the way around the Earth here and come back and make a newer point of closest reach and then go all the way around the Earth again. Whereas in the setting of the patch, where I'm allowed to come inside and outside, the way in which the process hits the patch is pretty much the same as the way a one-dimensional stable process will hit the origin. So the way in which a one-dimensional stable process gets close to the origin, sorry, not hits the origin, but gets close to the origin, is it kind of dances around the origin. It oscillates, if you like. I won't say oscillate in the strict sense, but it dances around the origin and it gets closer and closer. Eventually it goes off to infinity because we've got alpha between 0 and 1. But if I put a strip around the origin, oops, in a different color, if I put a tiny strip around the origin, then it will enter that strip by dancing around the strip and eventually passing into the strip. And so the same is going on in higher dimension. Let's just clear that away. The same is going on in higher dimension. The process is dancing around the patch, and then eventually it's entering the patch. So when the patch is really thin, I'm really getting a very, very localized view on things so that the Earth looks flat, of course, so I can apply flat Earth theory. And so fundamentally, the whole thing collapses down to a one-dimensional problem, as indeed we've seen in the way that I analytically treated the problem. I think this is the end of the talk.
Thank you very much. Thank you, Andreas. Very nice talk. We have got time for questions, so please, if you wish to ask one, unmute yourself and go ahead.
So maybe I can start with a silly question, Andreas. In the second part, you ruled out alpha bigger than 1 because you hit with positive probability.
Yeah.
Does that just mean that you therefore don't have to take limits? It's something which is...
Exactly. Yeah, I'm just restricting to that part of the conditioning would be just restricting to that part of the probability space. Right. And so it's a, you know, it's a trivial conditioning. So it's not that I can't condition it, it's just not that technically interesting.
Easy.
Okay. Any further questions?
Yeah, sorry, just another kind of silly question. So then for Brownian motion, the kind of analog of these results is already known, or?
No, actually. Oh. So we did all this, and then I kind of had exactly that thought. So the second problem where it comes in and out of the sphere, that doesn't happen for Brownian motion because it's got continuous paths. But the first problem, I assumed somebody had done it somewhere. When I went digging, I couldn't find it. So the results also in principle contain the Brownian setting, although I must admit, I've never actually sat and double checked everything we did, but because with things going Brownian, I don't think much changes, but I haven't actually sat down and just double checked everything, whether I was using something that was specific to stable processes, but I doubt it.
Yeah. No, I mean, so in like 3 dimensions, you would have the radial part of Brownian motion would be a Bessel process, and then decompositions of the minimum and stuff are all very well known. So presumably these kinds of things would work, yeah.
And it's even better because you get decoupling in that case. So all the way back, if we whiz back to where I spoke about, it was this slide, wasn't it? So in the setting of Brownian motion, what's even nicer is that there's a complete decoupling of these two processes. So this is even independent of this guy here. So this, as you say, this whole thing here becomes the Bessel D. It depends on how you learn that, where your parameters are, but this is the Bessel D, and then this is just it's a Brownian motion time changed on the sphere, but it's completely independent of that. Now, for a stable, that's not true. There's dependency between those two things. That's why it's Markov additive. But the Brownian has the even more convenient property that they're independent.
Okay, yeah, that's what it seems like. It should be easier, really.
Okay, thank you. Any further questions?
Andreas, I seem to remember some work of Harry Keston on coming in from infinity and hitting the sphere or hitting some points. I'm not sure if that's relevant here, but maybe it is.
Yes, it's very relevant, yeah. So that belongs to a cluster that must have been quite a way back, right? Maybe in even the 60s, is that possible?
Yes, sure, yeah.
I don't want to...
yes, let's not go, no need to go there, yeah. Andreas.
But it is very relevant because that comes back to the discussion we had here. So there was the paper of Harry, and then there was some more that I think Port wrote some stuff, but I think the story kind of got finished, if you like, by a paper of Blumenthal, Gator, and Ray. And in that paper, they I should mention also, Kostya, Rogozin as well in one dimension. So in one dimension, a sphere is an interval. So that was Rogozin's work. He looked at the first hitting into the unit interval. And then the Americans dealt with the sphere, and they looked at the position of first entry into the sphere, which of course included, when you kind of take the starting point all the way out to infinity, it gives you a harmonic function of some sort. And this is really important because, in a sense, you know, if you remember what I was saying, my excursions, I start from some x, so I put the sphere that passes through that x, and I want to enter that sphere. So in a sense, although I'm starting on the boundary of the sphere and running it until I enter the sphere, I mean, as you well know, if I know how to start just outside the sphere and then pass into the sphere, which is exactly this cluster of papers we were talking about, then I can construct the excursion. That's enough for me to build the excursion where I actually start on the sphere that I'm passing into. So it's extremely relevant. It gives the boundary, it gives the kind of the foundational work that allows me to build the excursion theory.
Mm-hmm. There also seems to be some connection with something else we know well. That's the creeping problem for, well, Lévy processes in particular. That is whether they land on the point as they pass through it or not.
Exactly, yeah. That's another great point, because in this case, with it being stable, you always jump into the sphere. So we never pass into the sphere by creeping through it. That means by actually hitting the sphere. A stable will always jump through into the sphere. I've got that luxury. That's for all alphas. Of course, if I started to reanalyze this problem with a different Markov additive process, because of course there's a very specific Markov additive process that gives me the alpha stable, I'd have to be a bit more careful about that. But in this case, I've got that luxury. And again, that's something we learned going all the way back to the 60s and 70s from this cluster of papers about stable processes that taught us a lot about passing thresholds, going into intervals, going into spheres, and all that background plays out here.
Okay, thank you. Any further questions? There might be no further questions. Andreas, thank you so much again, dedicating part of your beautiful morning to give this seminar. Thank you so much, and
thank you. Well, thank you for having me.
A safe move, comfortable enough.
Yes, indeed. Okay, thank you very much, everyone. I hope to see you
everyone.
all again
Thank you.
soon.